Welcome to the second part of Module 6. The learning outcomes of the second part of Module 6 are to balance general chemical equations, identify the oxidation number of elements, and balance oxidation reduction equations. We define a chemical equation as a shorthand expression for a chemical change or chemical reaction that shows the reactants that go into the reaction and the products that are produced by the reaction. In a chemical reaction, atoms are neither created nor destroyed. All atoms present in the reactants must all be present in the products. We write the reactants on the left side of the equation. The arrow shows the direction of the reaction to the products. The products are written on the right side. We also include the state of matter for the elements by using letter abbreviations. For instance, S refers to solid, G to gas, and L to liquid, and so on. For example, when you add aluminium to iron 3 oxide and heat the reaction, you get iron liquid and aluminium oxide solid. Because we need to heat the reaction, we include a small triangle over the arrow to indicate heat. Now, the main task when writing a chemical equation is to balance it. For example, AgNO3 plus H2S forms Ag2S plus HNO3. This chemical equation is unbalanced. To balance the equation, we need to put numbers in front of the compounds to make sure that we have the same number of elements on both sides of the equation. So the number of elements that are going into the reaction should be equal to the number of elements that are produced in the products. Let's look again at the example. We have 1 silver on the right side, but we have 2 on the left side. To fix this, we add 2 in front of the silver nitrate compound. Now we have 2 silver atoms on each side. The second element is nitrogen. Because we added 2 in front of the silver nitrate, we now have 2 nitrogens on the left side. We only have 1 nitrogen on the right side. So we add a 2 in front of the nitric acid compound. Now we have 2 nitrogens on both sides. Let's check the oxygen. Originally we had 3 oxygens in silver nitrate, but because we added 2 in front of the compound to balance the other elements, we now have 2 times 3 equals 6 oxygens. In the right side we also have 6 oxygens, so that's balanced. In terms of hydrogen, we have 2 on either side of the equation, so that's also balanced. The final element is sulfur. There is 1 on each side. So the equation is now all balanced. Let's look at example 2. C4H10 plus O2 forms CO2 plus H2O. This is also an unbalanced reaction. For this chemical reaction, there is oxygen by itself, so we will leave it until the last step. We start with carbon. There are 4 carbons on the left side, but only 1 on the right side. So we put a 4 in front of the carbon dioxide. Now hydrogen. We have 10 on the left side, but only 2 on the right side. So we put 5 in front of the water. Now hydrogen is balanced. Let's calculate how many oxygens we have in each side. On the left side we have 2. On the right side we have 8 oxygens from the carbon dioxide and 5 oxygens from the water. So we have in total 13 oxygens on the right side. We need to add 6.5 in front of the O2 molecule to balance the equation. However, we can balance equations using whole numbers only, so we cannot put 6.5 in front of the O2. To overcome this problem, we multiply everything by 2. So now we have 2C4H10, 13O2, 8 CO2 and 10 H2O. Check each element again and you should obtain the same number on each side of the equation. So there are 8 carbons on both sides, 20 hydrogens on both sides, and 26 oxygens on both sides. So the equation is now all balanced. Other examples will be covered in the weekly exercises and face-to-face tutorials. The chemical equation provides many important bits of information, such as the reactants and products as well as their formulas, the number of molecules or formula units in the reaction, the number of atoms of each element involved in the reaction, and the number of moles of each substance. Let's look at the following reaction. C3H8, a gas, plus 5O2, also a gas, forms 3CO2, another gas, plus 4H2O, gas. The numbers in front of the molecules indicate how many molecules are going into the reaction and how many are produced. For example, there is 1 molecule of C3H8, 5 molecules of O2, 3 molecules of CO2, and 4 molecules of water. You can also calculate the number of atoms involved in the reaction. We can calculate the number of moles for the compounds in the reaction. So instead of using the number of molecules, we use the number of moles. In this example, 1 mole of C3H8 reacts with 5 moles of O2 to produce 3 moles of CO2 and 4 moles of water. This is called the molecular ratio or the molar ratio. From the number of moles, we can calculate the mass by using the molar mass. For example, with C3H8, the molar mass is 44.09 grams per mole. So the mass is 44.09 times 1 equals 44.09 grams. For O2, the molar mass is equal to 32 grams per mole. We have 5 moles, so the mass is 32.5 equals 160 grams. Carbon dioxide has a molar mass of 44.01 grams per mole. We have 3 moles, so the mass is 132. And water has a mass of 72.08. You can notice that the total mass of reactant equals 204 grams. The total mass of products is also 204 grams. Remember, in chemical reactions, we don't create or destroy mass. However, the number of molecules or number of moles doesn't have to be the same as we are creating new compounds. Let's move on to the different types of chemical reactions. Reactions are classified into types to assist in writing equations and in predicting other reactions. A combination reaction is where 2 reactants combine to give 1 product. For example, 2Mg plus O2 forms 2MgO. SO3 plus H2O forms H2SO4. In a decomposition reaction, a single substance is decomposed or broken down to give 2 or more different substances. For example, CaCO3 is broken down to form CaO plus CO2. 2KClO3 forms 2KCl plus 3O2. Another type of reaction is called displacement, which can either be single or double. In a single displacement reaction, 1 element reacts with a compound to replace one of the elements of that compound. For example, zinc plus 2HCl forms H2 plus ZnCl2. 2Al plus 3H2SO4 forms 3H2 plus AlSO4 3. Al2SO4 3. In a double displacement reaction, two compounds exchange partners with each other to produce two different compounds. For example, HCl plus NaOH forms NaCl plus H2O. CuO plus 2HNO3 forms CuNO3 2 plus H2O. The last type of chemical reaction is the oxidation reduction reaction, known as redox. This type of chemical reaction involves the transfer of electrons between reactants. We will investigate this type of reaction in more detail next. The nature of redox reactions involves the electron transfer from one molecule to another. To determine which element lost electrons and which element gained electrons, we need to calculate the oxidation number. The oxidation number of an atom represents the number of electrons lost, gained, or unequally shared by an atom. Oxidation numbers can be 0, positive, or negative. There are rules to calculating the oxidation number. All elements in their free state, uncombined with other elements, have an oxidation number of 0. Examples being sodium, copper, magnesium, hydrogen gas, oxygen gas, chlorine gas, and nitrogen gas all carry oxidation numbers of 0. Hydrogen has a +1 charge in 95% of examples, except when it joins metals and forms a hydride ion. Examples: NaH and CaH2. Oxygen has a -2 charge, except in peroxides where it forms -1 ions. The other exception is OF2, where it forms a +2 ion. Oxidation numbers of an atom in a monoatomic ion equals the charge on the ion. For example, S2- has an oxidation number of -2. The sum of the oxidation numbers of the elements in a compound is 0. For example, H2O has a net charge of 0, as the oxygen has a -2 charge and the two hydrogens provide a +2 charge, so the total is 0. The algebraic sum of the oxidation numbers of the elements in a polyatomic ion is equal to the charge of the ion. Let's look at some examples in the next slide. So we need to determine the oxidation number of the following. The sulfur in SO4 2-. The total charge of the polyatomic ion is 2-. Oxygen has a 2- charge, so to calculate the sulfur oxidation number, we need to S plus 4 times -2 equals -2. So S minus 8 is equal to -2. Therefore, S must be +6. How about the oxidation number of sulfur in sulfuric acid, H2SO4? Notice that the net charge for the molecule is 0. Hydrogen is 2 times +1, so that is equal to +2. Oxygen is 4 times -2, which is equal to -8. So, +2 plus sulfur plus -8 is equal to 0. Therefore, the sulfur must be +6. How about the oxidation number of manganese in the permanganate ion MnO4-? Oxygen is equal to 4 times -2, so that equals -8. Therefore, the manganese must be +7. An oxidation reduction reaction, also known as a redox reaction, is a chemical process in which the oxidation number of an element is changed as a result of electron transfer. Oxidation occurs as a result of losing electrons, and the oxidation number of an element increases. Reduction occurs as a result of gaining electrons, therefore the oxidation number of an element decreases. To remember that, you can use the term oil rig. Oxidation is losing, reduction is gaining. To balance a redox equation, we need to follow certain steps in order. The order is very important to successfully balance the redox equation. The steps are: write the two half reactions that contain the elements being oxidized and reduced using the entire formula of the ion or molecule. To each half reaction, perform the following procedure in order. We must balance the elements other than oxygen and hydrogen. We then balance the oxygens by adding H2O. We can then balance the hydrogens by adding H+, as we are only learning redox reactions in acidic solutions. We then add E-, the electrons, to the side of the half reaction with a more positive charge. We can then multiply each half reaction by the appropriate number to make the number of electrons the same in each half reaction. Finally, we add the two half reactions together and cancel the electrons and any other identical substances that appear on opposite sides of the equation. Let's look at the following example and follow the steps to balance the equation. Balance the following oxidation-reduction equation in acidic solution. MnO4- plus S2- forms Mn2+ plus S. This equation shows an incomplete chemical reaction, as there is an O element in the left side but not in the right side. This is called a skeletal equation or incomplete equation. So the first step to balance a redox equation is to write the two half reactions that contain the elements being oxidized and reduced using the entire formula of the ion or molecule. So the first half is MnO4- arrow Mn2+. The second half is S2- arrow S. Before we continue on the steps, let's calculate the oxidation number to determine which half will undergo oxidation and which will undergo reduction. As we did previously, MnO4 has a net charge of -1. Oxygen has a -2 charge, so Mn should be +7. On the left side, Mn ion is by itself and has a charge of +2. So this is the oxidation number. So we can see that the oxidation number dropped from +7 to +2, which means that manganese gained 5 electrons. So this should be the reduction half. In the other half, S2- has an oxidation number of -2, and S is in its free state on the other side, so it has an oxidation number of 0. So the oxidation number increased due to the losing of electrons, and this half should be the oxidation half. If you are still not 100% sure about which half is the oxidation or the reduction, you can confirm that later when you balance each half equation. The second step to balance a redox equation is to follow this procedure for each half. We will start with the Mn half. First, balance the elements other than oxygen and hydrogen. There is one Mn atom on the left side and one on the right, so this element is balanced. Balance oxygen by adding H2O. There are 4 oxygens on the left side, but none on the right side, so we add 4 water molecules. Then we need to balance hydrogen by adding H+. There are 8 hydrogen atoms on the right side, so we add 8H plus to the left side. We then need to add electrons to the side of the half reaction with more positive charges. The total charge on the left side is plus 7. As the hydrogen ion has plus 1 charge, and we have 8 of them, that is plus 8. MnO4 has a minus 1 charge, so the total charge is plus 7. On the right side, the total charge is plus 2, and is coming from the Mn ion. The water has a net charge of 0. So to balance the charge, we need to add 5 electrons to the left side, as electrons have a negative charge. Now we repeat the steps for the second half. Balance the elements other than the oxygen and hydrogen. There's 1 sulfur atom in the left side and 1 on the right, so this element is balanced. Balance oxygen by adding H2O. There are no oxygens on any side, so we can skip this bit. Balance hydrogens by adding H+. Again, there's no hydrogens on either side, so we can skip this step. Then we need to add electrons to the side of the half reaction with more positive charges. The total charge on the left side is minus 2. On the right side, the total charge is 0. So, to balance the charge, we need to add 2 electrons to the right side, as electrons have a negative charge. The third step to balance a redox equation is to multiply each half reaction by the appropriate number to make the number of electrons the same in each half reaction. There are 5 electrons in the first half and 2 electrons in the second half, so the smallest common number is 10. Thus, we need to multiply the first half by 2 and the second half by 5. Remember that you need to multiply every element in the equation with the number, not only the electrons. So now the 2 half equations are 10E minus plus 16H plus 2MnO4 minus, arrow 2Mn2 plus 8H2O, and 5S2 minus, arrow 5S plus 10E minus. In this step, you can now confirm which half is the reduction and which is the oxidation. As the first half is gaining electrons, the electrons are in the reactant side, this half is the reduction half. In the second half, the sulfur is losing electrons, as they are on the product side, so this is the oxidation half. This confirms what we have predicted at the start of the example using the oxidation numbers. Also remember that you cannot have the electrons on the same side in both halves of the equation. The redox reaction happens due to transfer of electrons, so an element has to lose electrons for another to gain them. Now, the last step is to balance the redox equation. The last step in balancing the redox equation is to add the 2 half reactions together and cancel the electrons and any other identical substances that appear on opposite sides of the equation. Electrons are common on each side, so we can cancel them out. There are no other identical substances, so we can add both halves together now. The final balanced equation looks like this: 16H plus 2MnO4 minus plus 5S2 minus forms 2Mn2 plus 5S plus 8H2O. This is the summary of the redox reaction. You can do a checklist to make sure that there is an equal number of elements in each side of the equation using the following table. Hydrogen, there are 16 on the left side and 16 on the right side. There are 2 manganese on the left side and 2 on the right side. 8 oxygens on the left side and 8 on the right side. The total charge is plus 4 on the left side and plus 4 on the right side. As we have equal numbers between left and right sides of the equation, it is now balanced. We will practice more examples of redox reactions in the tutorial. This is the end of Part 2 of Module 6. Please proceed to Part 3, which will cover stoichiometry calculations.